Okay, this is Chapter 5, Section 1. There's only 3 slides in this particular one, and one of those is a video. We're going to talk about work, and we're going to do a few things with that, some practice problems too. It says work is done on an object when a force causes displacement of the object. What does that first bullet even mean? If it moves. So your object actually has to move. And work is done only when components of a force are parallel to a displacement. When the components of a force are parallel to a displacement. This last one, instead of me trying to explain exactly what that means, within a video that we're going to watch, they're going to show you how you can have a force that is perpendicular to displacement. Even though your object moves, no work is being done. So make sure you pay attention to that parallel part. You can have a force that's perpendicular to displacement. Your object can move, but no work will be done. And we'll see that in the video. In this one right here, it's showing a crate, and it's showing displacement, it moving along the ground, and it gives you a new formula. So you've got work, that's capital W, equals force times distance times cosine theta. And the force that we're looking at here is your net force. So if you haven't got your force into components, such as along the X and Y axis, you'll need to resolve. If there's an angle in play here, resolve your angle if you don't know the net force, but it is the net force.
So the F is net force?
Yes, it is net force.
So when does it need to be components?
If you're working, yeah. It depends on what information is given. You might not be given net force. You might be given some of the components.
Okay, and then you need to resolve it.
Yes.
Net force. Okay.
Yes. If it's not working with angle, then you've just got work equals force times distance. So what is going to be our unit for work? If it's force times distance, theta, that's going to be, the angle doesn't matter as far as units go. What is the unit for force? Okay. And what's the unit for distance that we're probably working with? Meters. So a Newton meter.
You said kilogram.
A Newton meter.
30 pounds for.
Do you mind?
Sorry.
A Newton meter is the same thing as joules. Capital J for joules. Joule. Now, you can leave the cosine theta in there. Let's just assume that you're pushing parallel to your surface and you don't have a push or pull that is at an angle. You tell me, if we looked at cosine theta, what is cosine of 0 degrees? So cosine of 0 degrees is equal to 1. That's why you can leave that in there. So cosine of 0 degrees is 1. What about cosine of 180 degrees? -1. And that could play a role. I mean, the negative is going to show you direction. If it's being pulled parallel but in the opposite direction. What is the cosine of 90 degrees?
0.
It is 0. So that's when you get into your force is perpendicular to direction of movement. And what we had looked at earlier said if it's perpendicular, then you really have no work being done. So all of this would cancel out if you had perpendicular type force to whatever direction you have where movement is taking place. So we'll watch the video and then we'll talk about.
Energy can be defined as the ability to do work. So to understand energy, you need to understand work. Work is the product of the force on an object, the displacement of the object, and the cosine of the angle between them. Since the cosine can be positive or negative, the resulting value for work can be positive or negative. For instance, if you pull a toy car across a level surface as pictured, the work is positive. The effect of your work should be to speed the car up. Notice that the force, if broken up into components, has a rightwards component. This rightward component agrees with the displacement of the car. However, if you pull as pictured here, you will tend to slow the car down. Since the force is to the left while the motion is to the right, the work done is negative. Again, the force and motion are in opposite directions here, so the work will once again be negative. The work will have the effect of slowing down the car. Here, the force and displacement are in the same direction again. Work is positive and the car speeds up. You can remember this two different ways. First, you can simply picture the force as being in the same direction as, or in the opposite direction to, the motion. Opposites are negative, so the work is negative when the force opposes the motion. Alternatively, you can visualize the angle between the displacement and the applied force. When the cosine of this angle is positive, the work done on the object is positive. When the cosine is negative, the work done on the object is negative. One last thing to remember is that when the force and the displacement are at right angles, no work is done.
So that last part is the bullet I was telling you about. You've got a work or a force here that is perpendicular to where displacement is actually at, so no work is done. I do want to go back and look at what they had on the previous one in case you didn't take any notes. They had a quadrant system set up here, and they had their car. Where does the 0 degrees start? Top, bottom, left, or right? Okay. The right side of the x-axis or the left side?
Right.
So 0 degrees here. Where does 90 degrees go? Top or bottom?
Top.
Top. So 90, 180, and 270. Thinking about the car that we had, it showed in this part over here that you had negative work, and on the opposite side you had positive work. So I need to know what is going on with force and your angle. Let's look at quadrant 1, positive work. How would you describe your angle?
Between 0 and 90.
Okay. And if you took cosine of that number, it would be positive, right?
Yeah.
Okay. And how would you describe the force that is applied? This is where he had the car and he was pulling a string in the direction that the car was going. It was also positive. Let's move over to the second quadrant. How would you describe theta here?
Negative.
It's negative. And how would you describe the force?
Negative.
Okay, this is where he was pulling the back end of the car with a force. Even though the car was going this way, he was pulling with a force in the opposite direction. Do me a favor. This is my car. He was pulling with a force in that direction. Okay? But it was actually moving forward. So it's negative. Let's go below that. You've got a car. And even though the distance is going this way, it's going in a forward direction, we were pushing down with a force in the opposite direction. How would you describe theta here? It's still negative. And what about the force?
Negative.
Still negative. And in the last quadrant, how would you describe theta?
Negative.
Put in cosine 300 degrees. I get a positive number. And the force here, this is, you've got your car going that distance, and you are pushing on it from the back. Also a positive force. So then that translates, when is work positive, when is it negative? Who's got questions? Because we're going to work through some examples. So there are 4 problems right here. We're going to work through all 4 of them. Start with number 1. Remember, pay attention to units as you're working through this stuff. The answer is 1.5 times 10 to the 7th joules. Yeah. So even if you were to work this on your paper or whatever, your calculator gives you proper scientific notation, but even if for some reason it doesn't, you should still put it back in proper scientific notation. Okay. Move on to the second one. So on this one right here, it's still force times distance. You do have a vertical distance of 2 meters. And the force that is exerted on the weights is parallel to it. Okay? The force exerted is parallel. So remember, work can be done if your object moves and the force applied is in the same direction as the movement. And in this case, it is. Let's take that one step further. What if he lifted the weights and then as he's holding them, moves across the room? How much work is done on the weights at that point?
Still 700.
It's 0. Okay? 700 newtons to get the weights lifted up, but once he has them right here, say on his shoulders, and then he walks across the room, from the point at which he starts walking across the room, no work is done on the weights. No work is done on the weights at that point.
I thought you meant like total, how much work was
No, no. Okay, go on to number 3. So I'm hearing an answer for number 3 of 1,586 what? Joules. So that is force times distance times cosine theta. The answer is 1,586 joules. Is work positive or negative in this example? It is positive. So the direction that you're actually pushing the cart and the force is in that same direction, it's going to be positive. Okay, let me pull up the last one. Okay, now you're working on number 4. Don't forget about units. Pay attention to units. You know, as I'm looking at what's given and what we're looking for, we know we want to use work equals force times distance, but we don't have force. How are you going to find force?
Mass times acceleration.
Okay. Mass times acceleration due to gravity. So use that first and then go back, plug in your information, and find the distance. When you get an answer, let me know. It's asking for distance, so your answer is 1.1 meters. 2 different steps in this one. 1.1 meters. You got to find the force first, and then you plug that in to your work equation and find distance. Look at the equation I've got marked as number 1.